Welcome to the lecture series of deep learning. Deep learning is a subset of machine learning that is finding its place in artificial intelligence domain in various horizons. Let us explore the various activation functions, architecture and the mathematics behind deep learning in this lecture series. So, in today's session, we will be seeing the introduction to deep learning. The agenda is history and evolution of deep learning will be explored, artificial neural networks, activation functions, the mathematics of neural networks and how we can train the neural network models will be explored in the session. So, the history and evolution of deep learning is that in order to appreciate the significance of deep learning today, we must be looking at the origins of deep learning. We have to understand that the concept of artificial neural networks dates back to the 1940s when the researchers began exploring how the machines could mimic human brain functions. One of the earliest models was called as perceptron. Okay. So, this perceptron was introduced by Frank Rosenblatt in 1958. Why? Because it was designed means in order to recognize the visual patterns and how it could classify the inputs based on the weights that is being learnt. But in spite of its promise, the interest in neural networks got vanished during the 1970s because of its limitations in the computational power and the theoretical understanding. There were a lot of challenges that was faced in this field, which included issues with convergence and the inability to solve linear problems. Okay. At this point, a turning point for deep learning came in the year of 2000s when several factors got converged like increased computational resources, availability of large amount of data sets and various advancements in these algorithms. Researchers began to develop deep neural networks which consisted of multiple layers that allowed for complex feature extraction and representation learning. Okay. So, we saw a lot of breakthroughs in various applications from image recognition to natural language processing, etc. So, in a gist, we have to understand that history and evolution of deep learning has seen its way back to 1940s. Next, we will be discussing about artificial neural networks. Here, as we said earlier, perceptron is one concept that will be dealt, and there is another concept called as feed forward networks. We have to understand that at the core of deep learning we have artificial neural networks. What is artificial neural networks? We all know that our nervous system consists of millions of neurons. So, the brain and the spinal cord and millions of neurons will constitute the nervous system that will make the human brain to function properly. In the same way, when we mimic the human function, we go to artificial neural networks. Okay. So, the simplest form of an ANN is the perceptron. It is consisting of a single layer of output node which is connected to input features. The perceptron will make decisions by weighing input signals and it will apply an activation function for what? For producing one output. Okay. So, while it can effectively classify the linearly separable data, its limitations became apparent. Why? Because the researchers wanted to tackle more complex problems. Hence, in order to address these limitations, the researchers developed feed forward networks. What will happen means, in a feed forward network, the information will flow in only one direction from input nodes through one or more hidden layers to the output nodes. There will not be any cycles or loops here. Every neuron in these layers applies one weighted sum, okay, which will be followed by an activation function to produce the output. This particular architecture is allowing for more complex decision boundaries and improved performance on a wider range of tasks. So, when you recollect perceptron and feed-forward network, we can understand that the artificial neural networks are functioning with the perceptron and feed-forward network as its core. Next comes the activation functions. So, when we go to activation functions, we have to understand that activation functions are playing a critical role in introducing the non-linearity into the neural networks. What is meant by non-linear concept? Linear means it is a straight line, non-linear means it will not be in a straight line. So, we have to understand that activation functions are brought into the picture. Why? Because we need non-linear aspects into our neural networks. These activation functions, what they will do means they will determine whether a neuron should be activated based on its input or not. Some of the common activation functions include sigmoid, ReLU, tanh and softmax. We have to understand that these are some of the common activation functions that are being used. Okay. So, the first one, sigmoid. This function will output the values between 0 and 1 only. What it will do means it will make it suitable for binary classification tasks, but it also suffers from vanishing gradient problem for very high or low input values. Next is our ReLU. ReLU means it stands for rectified linear unit. The short form is only called as ReLU. ReLU has become one of the most popular activation functions because of its simplicity and effectiveness. Its values will be, its outputs will be 0 for negative inputs and it will be linear for positive inputs. What it will do means it will allow the models to converge very faster while reducing the vanishing gradient issue. Vanishing gradient issue will be reduced in ReLU. Next is our tanh. The tanh hyperbolic tangent function is called as tanh. Hyperbolic tangent function, it will output the values between -1 and 1. It often performs better than the sigmoid function because it centers the data around 0 only. Okay. So, it will lead to faster convergence during the training processes. Next is our softmax. Softmax function is primarily used in multi-class classification problems. It converts the raw output scores called as logits, L-O-G-I-T-S, logits, into the probabilities. All these values will be added to 1 only. Okay, it will be summed up to 1. This will allow for easy interpretation of the data. This data will be interpreted in the form of class probabilities. So, deep learning is completely based on mathematics. We need maths in deep learning. From the basic to the advanced mathematics, we need all those concepts. So, let us see the basic concept in today's lecture and we will continue it in the further lectures. Neural networks will operate through linear transformations, okay, which is followed by non-linear activation functions. Every neuron's output can be expressed mathematically as one linear transformation formula called as y is equal to f of wx plus b. So, in this equation y is the output, w represents the weights, x is the input vector, b is the bias term, f is the activation function we discussed earlier, no, that is only f. F is the activation function which is applied to introduce non-linearity. So, here the training process will involve adjusting the weights based on how well the network performs on training data. In order to optimize the weights effectively, we need to compute a terminology called as gradient. Okay. So, the gradient essentially determines how much each weight is going to contribute to the errors that is going to occur in the predictions. So, this is the role of gradients. Next, we will see about gradient descent. So, here we have to understand that gradient descent is an optimization algorithm which is commonly used in training the neural networks only. Its primary goal is to minimize the cost function. What is cost function? Cost function is a measure of how well the network's predictions are going to match the actual outcomes by iteratively adjusting the weights. Okay, here we have several variants in the gradient descent. First one is called as batch gradient descent. Second one is called as stochastic gradient descent. Third one is called as mini batch gradient descent. Okay, so there are different variants in the gradient descent. First one, let us discuss about batch gradient descent. Why we need batch gradient descent means it uses all the training examples to compute gradient value before updating the weights. Okay. So, here it provides stable convergence and it can be slow with larger data sets. When it comes to batch gradient descent, that is the advantage. Next one, we will see about stochastic gradient descent. What stochastic gradient descent will do means it will update the weights using one training example at one time. Okay. This introduces noise into the updates, but it can even lead to faster convergence on a whole. Next, we have our mini batch gradient descent. This particular gradient descent is a compromise between batch gradient descent and stochastic gradient descent methodologies. This particular approach uses a small batch of examples for each update. So, here what will happen if it takes place in this manner means it will balance the speed and stability in an effective manner. That is the advantage of mini batch gradient descent when we compare it with the other two methods. So, next we have to understand how we can train one neural network. So, any neural network before it functions, we need to train it in order to make it function effectively. Okay. Yeah, so we have cost functions. So, cost functions are essential for evaluating how well a neural network is going to perform during the training process. They will quantify the difference between predicted outputs and the actual labels. So, there are two basic cost functions. One is called as mean squared error MSE. Second one is called as cross entropy loss. Why we need mean squared error means it is often used for the regression tasks. It will calculate the average squared difference between the predicted values and the actual values. When we go to cross entropy loss, it is commonly used for classification tasks. It measures how well the predicted probabilities are going to match the actual class labels. There we saw it is used for regression tasks. MSE is used for regression tasks, whereas cross entropy loss is used for classification tasks. Okay. So, here minimizing these cost functions through optimization techniques will help the improvement of the model's accuracy over time. Next, we are going to discuss about back propagation phases. So, here Backpropagation is one key algorithm which is used for training the neural networks in an efficient manner. There are two major phases in the backpropagation algorithm. One is called as the forward pass, another one is called as the backward pass. Okay. So, during the forward pass, inputs will be fed through the neural network layer by layer until one output is produced. Then what will happen means cost function will be computed on the basis of output compared to the actual labels. Second one, we have the backward pass. In the backward pass, gradients will be calculated starting from the output layer back through the each layers of the network using a functionality called as chain rule differentiation. We know, right, we have chain rule methodology in differentiation. So, using that only backward pass will be engaged. Then we have our gradients which is going to indicate how much each weight is going to contribute to the error. This will allow for targeted updates during weight optimization. By iteratively applying forward and backward passes across multiple epochs, epochs means the number in which the neural network is taking to perform in getting the outputs. It can be based on our need of the model. For example, if we set the epoch to 10, we will see that a number of epochs is running through 10. Okay, so complete passes through the training data set is called as epochs. Then we can see that the neural networks will gradually learn from the optimal weights, that is going to minimize the prediction errors. So, in backpropagation we have two passes, one is called as forward pass, another one is called as backward pass. Okay, so backward and forward pass both are equally important in training the neural network. So, if we take a summary of the lecture, we can understand that deep learning is representing a significant advancement in artificial intelligence, that is leveraging the artificial neural networks to learn from complex data structures in an autonomous manner. From its historical roots with perceptrons to modern deep architectures which are capable of solving intricate problems across various domains, deep learning is continuing to evolve in a rapid manner. So, we have discussed in today's lecture that evolution has seen its history from 1940s, and then it has seen lot of challenges, and then it has seen the advancements that we are enjoying today. So, we have to understand the linear transformations and gradients that are going to form the foundations for optimizing the network performance. We saw that training involves minimizing the cost functions using gradient descent methodologies, and it involves employment of the backpropagation algorithm for efficient weight updates. So, we have discussed all these things today. The current deep learning models are performing way back more than the older architectures. Okay. So, we are seeing that healthcare, transportation, medical and different domains, finance, etc. are seeing its employment. Due to its deep architecture, we can understand that, and the mathematics behind it is helping the deep learning models to perform in a way that is surpassing other architectures. So, we have to understand two things. We need a programming language that can converse between the various architectures that is present and the models that is present in this domain. So, we need Python programming language here. So, we have to be thorough in Python in order to implement the different models. That is the first point. Secondly, we have to understand the maths that is behind the deep learning models. So, these two, if we are thorough enough, we can easily cope up with the theoretical aspects. So, theoretical aspects is will be much simpler when we are understanding the crux of the field. We can make better utilization of the domain only when we are thorough in the maths and the programming of the deep learning models. So, we can continue them in the further sessions. Thank you.